Hello out there, this is Nicole Hemsoth, editor of HPC Wire, here with another in-depth interview session. Today we're going to be talking about Bayesian methods in high-performance computing and the future of both of those worlds. On the line we have Dr. Houman Owhadi and Dr. Clint Scovel, both from the California Institute of Technology. Hi, fellas.
Hey.
Hi, Nicole.
So Dr. Scovel has made significant contributions in the fields of symplectic integration algorithms, machine learning, and anomaly detection. And he's now focusing his attention on uncertainty quantification. So this has led him to a newer project, which we're going to touch on today, called the Scientific Computation of Optimal Estimators. So again, we're also joined by Dr. Houman Owhadi. He's a professor of applied and computational mathematics, control and dynamical systems at California Institute of Technology. He's focused on the modeling and analysis of systems that are characterized by uncertainties, noise, multiple scales, geometric structures. So we're dealing in uncertainties here. Okay. So in the context of high-performance computing, the two of you have argued recently that Bayesian methods are becoming even more popular than they ever were before to quantify uncertainty, both in science and industry. Let's spend a little while on the high-level concept here, and then we'll drill down on some of the specifics. So what is it about these methods that are necessary and even more necessary as we move toward ever more advanced systems?
Yes, well, Bayesian inference goes all the way back to a formula discovered by Reverend Thomas Bayes. And when he found that formula, Pierre-Simon Laplace took his research and developed it further into a field called Bayesian inference. And this started a 250 years old controversy. Now, what is the controversy about? In Bayesian inference, you have some prior about what reality could be. Then you condition your prior with some data that you observe. And this is basically the basis of the Bayes rule. Now, Pierre-Simon Laplace took that one step further where he said, okay, I don't really need to have an exact prior representing an exact measure of probability what corresponding to what reality could be. I can just make up a prior or belief about what reality could be. Then I can use Bayes' formula to update my belief. And this started the field that we know today as Bayesian inference. Now, in the 50s, Bayesian inference was mainly looked as a curiosity because we couldn't really compute those Bayesian posteriors for complex systems. But now with the advent of high-performance computing, we can actually compute those posterior probabilities. So, and since Bayesian inference is also an elegant and a simple way of combining information with our beliefs, they are becoming increasingly popular.
Excellent. And so, Dr. Scovel, to build on what he just said, HPC is so often considered to be about, full resolution, exact simulations that are as close to reality as possible. So where does uncertainty fit in the next generation of systems and applications?
Well, certainly no one believes that those systems compute exact anything. So there's always an error. And so having some confidence in what the results are is always going to be an interest. But I think the way that there's another way that these things fit together, and that is that not only does uncertainty quantification useful for high-performance computing, but high-performance computing is useful for uncertainty quantification, because that computation that he was saying that just came about in the 50s was basically our ability to do these numerical computations, in particular Markov chain Monte Carlo simulations to compute these posteriors.
Okay, interesting. And just to back up for 1 second, let's talk quickly about what areas of industry And to some extent, too, scientific computing, this is most important. So where is this most valuable?
Risk analysis, climate modeling. Take, for instance, Boeing. So when Boeing is developing a new airplane, most of their budget goes into the safety assessment of their new model. Now, what you have to understand with respect to that industry is that they have to certify that their new model of airplane has a probability of a catastrophic event that is smaller than 10 to the power minus 9 per hour of flight. Now, this is really small, and of course they cannot fly 1 billion of airplanes and just see how many crash. So they have to assess the safety of their system, but they cannot use Monte Carlo. So they cannot just use a frequentist estimate, and they have limited information. Take another example. You are JPL and you want to design your new satellite, and you want this satellite to go around the planet in the solar system, and you are spending a lot of money for it. How do you certify that your system is not going to crash? Now, one way is to build 1,000 of these satellites and just count how many crash, but that will be too costly, right? So you have to do it with very limited amount of data. And this has created a new field called uncertainty quantification, which is an emerging field. And it is basically a field that is at the interface between probability and statistics and computer science. And it mainly has to do with engineering system characterized by low number of samples, complex information. And so what you have to do is to, so the way we think that it should be pushed forward is basically to be able to process information in an optimal way, to assess the risk in an optimal way without making assumptions that may not be true and without ignoring relevant information. So let me explain. At the end of the day, our point of view is that you cannot really say if an information is valid or not, a piece of information is valid or not, or if a piece of data is accurate or not, unless you test it. But once this information is given to you or some expert opinion is given to you, the best thing that you can do is to process it in an optimal way. And basically what we are striving to do is to develop an algorithmic framework that will allow to do just that, process information in an optimal way. Now, you can imagine that there are plenty of places where you can apply these things.
Right. And Dr. Scovel, I believe this leads into your pet project right now, which is the scientific computation of optimal estimators. Where does that fit into this conversation we're having, and can you describe it more thoroughly?
Yeah, so when he was talking about doing this in the optimal way, the first question was, what does that mean? And so instead of providing solutions, well, the first thing that we do is actually formulate a problem that incorporates the customer's objectives, that they're interested in the available information, what we know about the information, what the domain experts know about the information, etc. And then you formulate this optimization problem, which essentially defines what it means to be an optimal solution to this question that you're asked, like how reliable is that satellite going to be? And where this is new is that historically what has been done is you provide some model for this process, and then you see what happens with the model. Ours is different. We're saying we want to formulate this problem that we're trying to solve, and we're going to use our computing capability, in particular high-performance computing, to solve these problems, which think historically, that's very similar to Bayes' method in the past, is historically the reason why people didn't go down this path is we didn't have the computing power to do it. But I think we now do have the computing power to actually solve these problems, defining optimal estimation problems or optimal prediction problems, given optimal being optimal over some set of assumptions that we're all willing to agree on.
Right. And so I noticed that both of you have, just in your body of research, you've all talked a little bit about exascale, solving exascale class problems. So those are the types of systems you're looking at to be able to do this at a much higher level. Is that correct, or is that?
Yes. So I could take an analogy here. 200 years ago, if I were to ask you to solve a partial differential equation, you wouldn't use the computer. You would probably use your brain. And you would probably need the expertise of a Cauchy or Laplace to do that. And you will probably not come with a quantitative estimate of the solution, but only qualitative estimates. Now, if I ask you the same question today, you will not use your brain to solve the partial differential equation. You will use a computer. But you will still use your brain to program the computer that will crunch numbers for you to solve the partial differential equation. And this paradigm shift can be traced back to seminal work by John von Neumann and Goldstein in the 50s, and to humans organized as computers in the beginning of the century, of the previous century. Mm-hmm. Now, today, if I ask you to find a statistical estimator, or to find the best possible climate model, or to find a test that will tell me if some data that I'm observing is corrupted or not, you are not going to use a computer to do that. You are going to use your brain and guesswork. Now, what we want to do here is basically to turn this guesswork into an algorithm that will be able to implement on a high-performance cluster. Now, and if you look at the mathematics behind this problem of turning the process of scientific discovery into an algorithm, you can basically translate it into an optimization problem, but the optimization variables are not discrete. Okay, they are not zeros and ones. They are basically infinite dimensional objects. And what we have found is a new form of calculus that allows us to turn these infinite dimensional optimization problems into finite dimensional optimization problems that we can start solving on computers. Now, even after reduction, these optimization problems are extremely large. So that's why we believe that we're going to probably need exascale machines or petascale machines for solving this kind of problems for complex systems.
Mm-hmm. What's interesting in that conversation about the systems required, I recently talked to, I believe, the only quote quantum computer company, D-Wave, recently, and this exact type of optimization problem, this best of both worlds or of all worlds solution, is exactly the sweet spot for quantum computers. Do you believe that those actually exist, and if so, are they a good fit for the types of problems you're seeking to solve?
This is interesting because with respect to exascale machines, some people believe that there are two ways to approach high-performance computing. The first way is just to solve the same kind of problems, but bigger problems. So, for instance, if you're interested in climate modeling, you're still going to do climate modeling. You still are going to run your model, but with a finer mesh, with a finer resolution, and hopefully, instead of predicting the weather for 4 days ahead, you will be able to do it for 5 days ahead. What we envision here is some kind of paradigm shift where instead of numerically solving a bigger model, you actually use your computer to find the model itself. So yes, if there are quantum computers out there, that would be a great thing for this new kind of framework.
Yes. So if I may chip in here, so if the more computing power we can have, the better our success is going to be there.
First, you see, information that doesn't necessarily come in the form of 0 and 1s. You see, I mean, if you look at the underlying optimization problems, they involve optimization variables that are measures of probability and functions, and these objects live in infinite dimensional spaces. And calculus in a computer is necessarily discrete and finite. So the first step of the technology is mathematical. You have to be able to manipulate to come up with a new form of calculus that is able to manipulate these infinite dimensional objects. And this is basically what we have done. And this new form of calculus allows us to take these huge optimization problems and turn them into something discrete and finite that we can start solving on a computer.
But it's also more than that, in the sense that it's not just a question of computing power. Part of this program and this paradigm shift we're talking about is actually coming up with the formulation of what it means to be an optimal solution to these things.
Yes.
That's actually a big part of the program. It's not just I know what I want to compute and I need more computing power. It's actually what do we want to compute and what does it mean to be the best? I think the complexity involves in the formulation of these problems, and these formulations of these problems of what it means to be an optimal predictor or an optimal estimator requires communication from all levels of the effort, from the customer to the project leader to the domain expert, the material science domain experts, the statisticians. Instead of, for example, in many places, you do a bunch of runs, you do a bunch of modeling, you do a bunch of stuff, and then you hand all the results off to your statisticians and you want them to put that stuff together. We're saying, no, you need to do that all together. You need to have everybody communicating, so you formulate not only what the objectives that you're interested in, but you formulate what pieces of information you have good confidence in about, and those establish a quantitative set of realistic paradigms, and then the optimization is now proceeds as, okay, now we have this huge optimization problem. How do we reduce it analytically? How do we take those reduced analytic problems and how do we implement them on the computer, and how do we know we're done? That's sort of the picture.
Let me give you two examples here. Okay. The first one will be investing in the stock market. Question: is there an optimal way to invest in the stock market? Now, currently it's not clear how to turn this into an optimization problem. But with the framework that we are developing, we think that we'll be able to turn this problem into an optimization problem and reduce it to something that we can start solving in a high-performance cluster. And the idea is to invest in an optimal way given the limited information that you have at hand. Let me give you another example. Consider the game of chess, right? We have computers playing chess, and they play chess very well. Now, question: can you have a computer play an information game or an information war? So, for instance, you have two armies, and they are playing this information war, or you have two companies, and each company has limited information about the other company, and they have some decisions to make with respect to what their other company could or could not know and could or could not do. And if you look at it, this is just an information game, but the board is not just composed of 64 squares, and the moves are not discrete. There can be anything, right? So if you want to start addressing this kind of problems, you need some new mathematics that allows you to manipulate these pieces of information that do not live on the chessboard. And this is basically the first step in our technology to develop this new mathematics.
Yeah, and on that note, where do you see this maybe revolutionizing certain approaches to computing down the road?
I think that eventually we will use computers to help the process of scientific discovery, but not just to solve mathematical equations, but to develop the mathematical equations themselves. So we see this going into the field of machine learning. Now, in the field of machine learning, if you want to develop an intelligent agent, you basically decompose the task that you ask the computer to do into small steps, and you choose the work for the computer. What this technology that we are developing will allow to do, and this is basically long-term vision, is give the ability to a computer to develop a model of reality, act on that model of reality, and update the model based on the feedback that it is receiving from reality. And this is basically a change in machine learning.
Absolutely fascinating work. Unfortunately, we are out of time. I look forward to pointing over to some of the work that both of you have done independently and as collaborators. Thank you very much for your time, Dr. Owhadi and Dr. Scovel.
Thank you.
Thank you very much, Nicole. It was a pleasure.